So chapter 1 started with the concept of function, and then we started going back and revisiting things we've seen before, like lines and absolute values, and sort of putting a functional layer on them. So today we're going to look at quadratics and look at quadratic functions, which is sort of the looking at functions whose graphs are parabolas. So once again, I expect you to have seen these at some point before, but we're going to go review the basics today and then talk about how they act as functions. So the word quadratic, anytime you see the word quadratic in mathematics, that means second power. Just like linear last week means first power, quadratic means second power. And there's two standard ways you're going to encounter quadratic functions. There's the general form, and here's the general form. ax squared plus bx plus c, where a is not 0. So the specification here that a is not 0 means that you actually have an x squared in there. If you don't have an x squared in there, then it's either a linear function or a constant function. So this stipulation is just letting you know that there is a quadratic term. It's a quadratic function. In this, you may remember this is how they typically phrase like the quadratic formula. ax squared plus bx plus c is 0. And then they give you a little formula for that. And we'll review that here in a minute. The so-called standard form of a quadratic is this form. And you may recognize this. This is the completed square version of this. And notice it kind of looks like what we did last time. A absolute value x minus h plus k. So that's what we talked about last time, where we got a absolute value function. That gave us a v. But hopefully you remember that when you graph a quadratic equation, you're going to get what's called a parabola. Now we're going to revisit parabolas, and we're going to revisit completing the square in chapter 7. Okay. So what we want to do today is just use what we know about parabolas from the old days, not necessarily go back and rederive anything. Because once again, we're going to be looking at that again in more detail in chapter 7. But something I want you to think about as we move through today is this: the standard form for quadratics versus the standard form for absolute values. The only difference between these forms is here we're squaring the quantity, and here we're taking the absolute value of the quantity. But it turns out a lot of the stuff that we know about the absolute values still works for quadratics. So what do I mean by that? Well, let's take a look. So if you've got your quadratic function in the form f of x equals a times the quantity x minus h squared plus k, just like the vertex was hk for the absolute values last week, guess what? The vertex is hk for the parabolas this week. We have the axis of symmetry just like we did with the absolute values. If a is positive, the parabola opens to upwards. A is negative, it opens downwards. When it opens upwards, we have a minimum. When it opens downwards, we have a maximum. So once again, except for the shape, which the absolute value has a V shape to it, except for the shape, this is the same result we had about absolute value functions. So here's a summary of formulas. These are things that, once again, I expect you to have seen at some point in the past. If your parabola is given to you in the standard form, you can quickly read off the vertex. And when you want to solve for f of x equals 0, in other words, if you're trying to solve for the x-intercepts, then solving for that isn't bad. You isolate the perfect square and then extract square roots. If, on the other hand, your quadratic is given to you in the general form, then we have the vertex formula, which you may remember. The vertex formula gives you the x value of the vertex. It's the opposite of b over 2a. To get the y value, well, how do we always get the y value on the graph of a function? We plug that into the function. All right. Now, there is a formula for the y value, but it's not worth memorizing. The opposite of b over 2a, that's pretty quick to get. You plug that into the function. That's how you get your vertex this way. And to solve f of x equal to 0, you always try factoring if you can. Otherwise, there's your quadratic formula. Now, if you're interested into where the vertex formula and the quadratic formula come from, we go through in the book talking about completing the square. The beginning of the semester tends to be hectic enough with all sorts of things going on besides the actual mathematics. Even in a normal semester, I typically delay completing the square till chapter 7. So when we get to chapter 7 and we're more comfortable completing the square, we can always come back and fill in these details. All right. But for now, hopefully the vertex formula and the quadratic formula are familiar to you. And we're going to be reviewing them as we go through our examples today. So most of our examples today are going to be straight up, here's a quadratic function, let's graph it, find the parts. Where's it increasing, where's it decreasing, what's the domain, what's the range, that kind of thing. So our first example, f of x is equal to 2 times the quantity x minus 1 squared plus 3. This is exactly in the form a times x minus h squared plus k. All right, this is exactly the standard form here. And so I can read off the vertex in the same way I read off the vertex from absolute values last time. You take the opposite of what's in there. So you see a minus 1, that's going to be a 1, and then 3. So there's your vertex. Find f at 0 and use this to find the y-intercept of the graph y equals f of x. So f of 0 means everywhere you see an x, you're going to replace it with a 0. So the subtraction happens inside the parentheses first. Then the exponent happens. Negative 1 squared is 1. The multiplication, 2 plus 3, then is 5. So the y-intercept is the 0.05. Show the equation f of x equals 0 has no real solutions, and explain why this means the graph of y equals f of x has no x-intercepts. Well, just a second here. The cat keeps pretending she wants to come inside, but all she wants to do is me come open the door. All right, so let's do this. So when you have a quadratic equation this way, once again, you've got this x in here. We're subtracting 1 from x, then we're squaring it. We're multiplying by 2 and then adding 3. So if we want to try to get back to the x, we have to reverse everything that's been done to it. So we can subtract the 3 over. We can divide the 2 over. And now we're stuck, because the next step would be to get rid of that square root by extracting square roots. Well, here's the problem. That's a negative number. And you may recall that when you go to extract the square root of a negative number, that's no longer a real number, okay? Because anytime you square a real number, if you square a positive number, it becomes positive, or stays positive rather. If you square a negative, it becomes positive. There's no real number that you can square to get a negative number. In fact, you may remember that when you take the square root of a negative number, you get what's called an imaginary number. And we'll come back to imaginary numbers here in chapter 2, at the end of chapter 2. But for now, we just say there's no real solution here. No real solution, meaning no real number solution. And that means that there's no place where this function is 0. So the f of x then is never 0. And that means that the y is never 0, so that there's no x-intercepts. So when we graph this parabola, we don't expect it to ever cross the x-axis. It's either always going to be above or always going to be below. Any questions on that analysis there? Graph f of x using the vertex, y-intercept, and symmetry. Okay, so we're going to graph this thing. The vertex we know is 1, 3. The y-intercept we know is 0, 5. So we'll go 1, 3, 1, 2, 3. That's our vertex. The y-intercept was 0, 5. And we also know that the vertex, that acts as an axis of symmetry. The x value there acts as an axis of symmetry. So you notice that if you go up, you go over 1, up 2, over 1, up 2, there's going to be another mirror point. So that's using symmetry here to plot the point. Anytime you have one point on one side of the parabola, get a point on the other side, then you connect it up. And since this is a quadratic, you're going to connect it up using that parabola shape. So, drawing on the tablet is always more challenging than the board for me. So when in doubt, you draw what you can, and then you just label the word next to it parabola, and then no one will question you. Okay? All right, so the domain of the function, well, we know parabolas, they keep going up and keep going out forever. So that's going to give us a domain of all real numbers. As far as the range goes, if we're looking at the y values here, we start at the vertex 1, 3. So as far as the y values go, we start at 3, and then we get everything above 3. So that would be 3, including 3, with the bracket off to infinity. We use the range to help us figure out the maximum and the minimum. There is no maximum here because it goes on forever, so there's no maximum for this function. But the minimum is 3, because we've got 3 there included. Now, looking at where f is increasing, decreasing, constant, remember we're looking for x values here. So if I imagine coming in here from minus infinity, as I'm coming in, we have to imagine the parabola is going up and further to the left. So as I come in from the left, though, I'm heading down the parabola. So it's decreasing up to the x value 1. So minus infinity to 1. And then at x equals 1, it changes. And now at x equals 1, I'm starting to increase. And there's no places where it's constant because constant, remember, it levels off. So are there any questions using the graph to get the information about the function from the graph? Let's take a look at this next example then. F of x, negative 1/2, quantity x minus 1 squared plus 8. once again, we know it's a quadratic because of that second power there, so we know the graph's going to be a parabola. We're looking for the form x minus h squared plus k, which we've got. So I take the opposite here of the minus 1, I get a 1, 1, 8. It's going to be my vertex. Find f of 0, use this to find the y-intercept, so we're going to plug x equals 0 into the function. And once again, the subtractions inside the parentheses goes first. 0 minus 1. Negative 1 squared is positive 1. Times negative 1/2. Negative 1/2 plus 8. So this is going to be 7.5, which we could write as a terminating decimal 7.5. So the y-intercept then would be 0, 7.5. Solve f of x equals to 0 and use these solutions to find the x-intercept of the graph. Okay, so solving f of x equal to 0 here. Once again, I have only one x in this formula, and I work my way out. The last thing that's happened is I'm adding the 8, so the first thing I got to reverse or undo is subtracting the 8. I got to get rid of this multiplication here by the negative 1/2. I can do that by multiplying both sides by negative 2. So I get x minus 1 squared now as a positive 16. And now I'm going to extract the square roots here. X minus 1 is plus or minus the square root of 16. Don't forget the what? Plus or minus. You're trying to solve an equation here. So not only do you want the regular square root, which would give you the positive root, but also you want to make sure to capture the negative root. So don't forget that. The square root of 16 is 4. So x minus 1 is plus or minus 4. So then x would be 1 plus or minus 4. So 1 plus 4 gives us 5. 1 minus 4, negative 3. And so our x-intercepts then are the points 5, 0, negative 3, 0. Any questions on finding the vertex, y-intercept, or x-intercepts in this case? Okay, so here we are again. Graph the function using the vertex, y-intercept, x-intercepts, and symmetry. Vertex we had was 1, 8. The x-intercept was 0, 7.5, so it's right up there next to it. And the x-intercepts were negative 3, 0, and 5, 0. Okay. And now we're going to connect that with what shape? Well, it's a quadratic, so the shape's going to be that parabola. So let's see if I can manage this. That's a pretty terrible parabola. Go, and that comes down this way. Looks like I missed it there. We'll write parabola there. Now notice here the x-intercepts, we had negative 3 and 5. Right? Now notice if I take the midpoint there, if I take negative 3 plus 5 and divide by 2, where am I at? I'm right here at the vertex here at 1. Okay, so we have that symmetry there. So the domain, once again, for quadratic functions, the domain is going to be all real numbers. The range is determined by the vertex. So here the vertex was 1, 8. So looking at the y values, we get everything from negative infinity all the way up to and including the 8. The range then informs us as the max and the min. The maximum here is 8. That's the biggest y value we get out. We get there is no minimum because it goes down forever. And remember, for increasing, decreasing constant, we're looking at x values here. So if I imagine trudging along the x-axis from negative infinity all the way up to 1, we're heading uphill, so it's increasing. And then starting at 1 to infinity, we're heading downhill, so that's decreasing. And once again, there's never any place where it's constant. There's no horizontal lines. Any questions on getting the information about the function from the graph? Okay, so now it's time to kind of go backwards. Instead of here's the function, graph it, here's the graph, figure out the function. Find the standard form of the quadratic functions whose graphs are shown below. So we're kind of going backwards here. So remember, standard form means, f of x equals a times x minus h squared plus k. Once again, we know it's squared because we're looking at parabolas. All right? And they tell us it's quadratic. So, that's what indicates that. So, the h and the k typically usually easy to get because they help with the vertex. So let's take a look at the vertex here. See if we can try to approximate that. It looks as if the vertex appears to be at the point 2, 4 based on this graph. And so that gives us part of it now. F of x equals a times x opposite of 2, x minus 2 squared plus 4. So does everyone see how the vertex is giving us that h and k back? Now, last time when we had absolute value functions, we could get the h and the k from the vertex, and then we would get the a using a slope. Well, a doesn't represent slope anymore. Slope applies to linear things. Slope applies to lines, and the absolute value function was more or less 2 lines glued together. Here, we don't have lines, so we need another strategy. And this strategy is the more general strategy to doing this. And you can use this strategy with what we did last week as well to help us determine a. Because ultimately, I can go back and look for points on the graph and use them. So if I use a point other than the vertex, it looks pretty clear. Say, for example, that the graph goes to the point 4, 0. So that means that when x equals 4, y equals 0. Right? In other words, when x equals 4, f of x equals 0. In other words, f of 4 equals 0. So this goes back to the second day of class, the end of the first week. Okay? So that means what I can do is take my expression f of 4 and plug 4 in for x. So that'd be a times 4 minus 2 squared plus 4, and that has to be equal to 0. So we're plugging x in to here. And then setting it equal to 0. Does everyone see what's happening there? And now notice the only variable here in this equation is a. So once again, I can go through. The subtraction happens first. 4 minus 2 is 2. 2 squared is 4. So I get 4a plus 4 is 0. Subtracting the 4 over, I get 4a is negative 4. Dividing by that, we get a is negative 1. And so my formula here is negative 1 x minus 2 quantity squared plus 4. That would be my final answer. And once again, the ultimate check is to graph it. Get the vertex at 2, 4. Plug in 4, see if you get 0. Boom, you're done. So any questions on that? Vertex will give you h and k. And then another point on the curve will help you with finding a. Here's the graph, y equals g of x. Once again, we're looking at standard form, g of x equals a times x minus h quantity squared plus k. Excuse me. It appears as if the vertex is the point 0, negative 4. So now we're down to that point, and now we want to use another point on the curve. So we could pick 4, 0 again. That means that g of 4 is 0. So when I plug 4 into my formula, it better work out to be 0. 4 squared is 16. 16 times a minus 4 is 0. Add the 4 over. Divide by the 16. We get a is a quarter. And so there's my final answer. So vertex gives you the h and the k. Plug in another point on the graph to help you work backwards to find a. And if you want, you can go back and rework what we did last week with absolute values. And instead of using slope to get a, plug in a point on the graph and solve for a. Once again, this is the more general method moving forward. We're going to see this again in the next few chapters when we're trying to get a formula for a curve. We'll often exploit some structure. In this case, we're exploiting the vertex structure. But then we'll have to plug in a point to get some other missing variable. Okay, the next couple of examples, the quadratic functions are given to us in the general form, not the standard form. That means that there's more work to do to find the stuff. All right, and this is a great opportunity to review some of this stuff you probably saw back in Algebra 2. So remember what the general form looks like it's ax squared plus bx plus c. And so here, the x squared is always written first. So I'm going to write that as a opposite, negative x squared plus 6x. And so if we wanted to be pedantic about this thing, we'd write this as a negative 1x squared plus 6x plus what? 0. All right. So now since we're not in the standard form, we're in the general form, we've got to use that vertex formula. So the vertex formula, x equals the opposite of b over 2a. That's going to be the opposite of b, which is the coefficient of x. So that's 6 over 2a. A is the coefficient of x squared. That's negative 1. So you go through the machinations here. You get negative 6 over negative 2. That's a positive 3. Now, that's the x value of the vertex. To get the y value of the vertex, we plug in x equals 3. So the way you get y's on the graph of functions is you plug them in. So we got 18 minus 9, which is 18. Excuse me, 9. So the vertex then is 3, 9. And once again, hopefully somewhere in the past you remember doing this sort of thing to get the vertex of a parabola. Find f at 0 and use this to find the y-intercept. So where is x equal to 0? Let's plug that in. You get a whole bunch of zeros there. And so we get our y-intercept is 0, 0. And guess what? That's also a what? Not only is that a y-intercept, that's also an x-intercept. So speaking of x-intercepts, let's find all the x-intercepts. But before we move on, are there any questions over the vertex or the y-intercept? So now let's find the other x-intercepts by solving the f of x equal to 0. So we have a quadratic equation. Notice we have x in more than one spot. So if you have x in more than one spot, then you want to try factoring, or if that doesn't work, you could always whip out the quadratic formula. Here we can factor an x out of both terms pretty quickly, and then we can split it. We have two things multiplied together that give me 0. We have x and we have 6 minus x. Make sure you're always factoring against 0. Right? Because we have a property of the real numbers. If you have two numbers that multiply that give you 0, the only way is if one or the other or both are 0. So either x is 0 here, or 6 minus x is 0. The x equals 0 we already knew about. Here we get x equals 6. So we get the 0, 0 intercept we had before, but we also get the 6, 0. And so with our vertex, our intercepts, we can now sketch a reasonably good graph of our parabola. So the vertex was what? 3, 9? The y-intercept was one of the x-intercepts, 0, 0. 6, 0. It's a quadratic, which means it's going to be what shape? Parabola. Let's see if I can manage it. Well, that's not bad. I'm going to put the word parabola there to cover myself. Now, once again, you can check all this on Desmos. All right, maybe we'll check this one on Desmos just to show you. But you want to get good at recognizing, oh, that's a quadratic. It's going to be a parabola. It's going to open downwards, that kind of thing. Domain, once again, for these quadratic functions, the domain is everything. This parabola will continue to head down and doing that spread out. It'll spread out left and right infinite, minus infinity to infinity. The range, of course, is determined by the vertex. The vertex was up here at 3, 9. So looking at the y values, I'm going to get all the y values up to and including that 9. The range tells us the max and the min. The max is the biggest y value on the graph. That's 9. There is no minimum because it goes to negative infinity. Remember, for increasing, decreasing, and constant, we're looking for what? We're looking for x values. Here we come. Coming in from minus infinity, the parabola is rising. We're heading uphill. That means we're increasing from minus infinity to 3. Well, once we get to x equals 3, then things start to head downhill. 3 to infinity. Any constant? Any places where it's a plateau? No, none. So there it is. Any questions on graphing the parabola? And once you get the graph, listing the analysis. All right, once again, hopefully it's coming back to you, these things. All right, here, yet another one, right? You got how many more of these? You got a few more of these. Once again, this is what we call the general form of the parabola. It's given to us, instead of just a perfect square, we've got an ax squared plus a bx plus a c. The vertex formula here gives us the x coordinate, negative b over 2a. What's that going to be in this case? The opposite of b. B is the coefficient of x. So notice that's going to be a what here? That's a negative 3. Don't forget the negative. The a is the coefficient of x squared. And if there doesn't appear to be one, it's because it's being multiplied by 1. So we get our vertex here, x equals 3 again. How do we get the y coordinate? We plug it, the x in to the function. We get a 9 minus a 9 minus a 4. So the vertex, 3 comma, I take that back. I take that back. What did I forget to do here, folks? Uh-oh. What did I forget to do? I can already see the YouTube comments going nuts. It's 2a. So we get 3 halves. We get 3 halves there. So I got to put 3 halves in. I thought that was going a little too clean for an example this late in the handout. All right, let's put the 3 halves in. Here we go. Let's remember how fractions and powers work. If you take 3 halves squared, 3 halves times 3 halves. So you're going to get 3 times 3 is 9 in the numerator, 2 times 2 is 4 in the denominator. The power, remember, on fractions goes to both, numerator and denominator. Here what happens is I'm taking 3 times 3 halves. Think of that as 3 over 1 times 3 halves. That 3 only multiplies the numerator, and I get 9 halves minus 4. And if we wanted to get a common denominator here, it looks like the common denominator would be 4. I'd have 9/4 there, minus 18/4 there, minus 16/4. So what am I left with when that's all said and done? I'd get a -9 out of that, a -25/4. So the vertex, one way to write it is 3/2 -25/4. But once again, these are both have terminating decimals, so it might be easier for you to plot it looking at 3/2 is 1.5. And what's 25/4? Minus 6.25. Okay, once again, as long as the decimal terminates, I'm fine with you using decimals. If it doesn't terminate, then any finite decimals you write down would be an approximation. Okay, any questions on the vertex there? All right, let's find f of 0. F of 0 means everywhere we see an x, we're going to plug in a 0. Now here's what's nice about the general form. Everything's going to cancel out except that value c, in this case -4. So that's usually quick to get. So the y-intercept at least is quick to get. And now we want to solve f of x equal to 0 and use those solutions to find the x-intercepts. So once again, we're setting y, which is the function, equal to 0. So x squared minus 3x minus 4 is 0. Let's try to factor that. The quadratic function will always work, but oftentimes factoring can be faster. So we need to unfoil this. And once again, if you want extra practice on this, let me know. There's handouts there under course content that will help you review the factoring. If you want, a direct link to those, let me know. I can email those to you. But the idea is we need two things that multiply together to give me x squared. Well, there's not that many of those. It's x and x. Now I need to think about things that multiply to give us a -4. The fact that it's negative means one's going to have to be positive, one's going to have to be negative. We needed them to add up to -3, so that means we would have a -4 and a +1. And we just do a quick check. X times x is x squared. We've got -4x plus x minus 3x minus 4. And now we've got two things multiplied together that give me 0. So I can split this. Either the x plus 1 is 0, or the x minus 4 has to be 0. So x is either -1 or x is equal to 4. And that gives us our two x-intercepts, -1, 0, and 4, 0. Any questions on getting those x-intercepts? X-intercepts live on the x-axis. The one thing I know about points on the x-axis is that their y value is 0. With functions, the y values are the function values. So here we go. Let's try to remember all this and put it together. The vertex was at 1.5, -6 1/4. So we're going to have to approximate that. 1.5, -6 1/4. So like down there somewhere. The y-intercept was 0, -4. The x-intercept was at negative 1, 0 and 4, 0. All right. And once again, if I average the x values here, I get the x value of the vertex. So before we had made that mistake, we would have found out about it pretty quick at this point. Now I connect the dots in a pleasing fashion. What's the pleasing fashion here? Quadratic means parabola. So here we go with my dodgy parabola here. And once again, just to cover it, we'll write the word parabola. All right, domain, once again, for the quadratic functions, domain's what? Everything. This parabola will continue to spread outwards forever. All values of x are going to have a point on the graph. The range, once again, is determined by the vertex here. The y values on the graph, they're going to start at negative 6.25, but then they'll go on forever. The range gives us the max and the min. Is there a maximum? No. Is there a minimum? Yes. All right, let's start. Imagine we hitch a ride on this graph. As we come in from negative infinity, the graph is falling up to the vertex. Where's the vertex again? 1.5. So it's decreasing. And then at 1.5 it turns around and starts to increase. And it's never constant. Never constant. Any questions on the graph or finding the bits from the graph? It's a lot of rinse and repeat, but it's important at this stage to rinse and repeat these things to make sure we understand these concepts, because they're with us. Anytime we look at any kind of function analysis, we're going to be asking for domains, range, maxes, mins, increasing, decreasing. And we'll see here at the end, the last example we do is an application. It's a profit. And we're going to be interested in knowing these things about profits. Do we have a maximum profit? Where is it? That kind of thing. All right. Here's our last non-word problem example. Once again, this is given to us in the general form. The general form is ax squared plus bx plus c. And so once again, we can be pedantic and rewrite this. What's multiplying the x squared is a negative 1. What's multiplying the x is a negative 2 plus c. We're asked to use the vertex formula to find the vertex. The vertex formula. Remember, the vertex formula, the opposite of b over 2a, gives us the x coordinate. So the opposite here, negative 2 over 2a. Don't forget the 2 like I did last time. So I get a positive 2 over a negative 2, which is a negative 1. Now, negative 1 is the x value of the vertex. Oh, we got the doggo here. Getting comfortable back there behind the desk. How do I get the y value? Well, I got to plug this in. Now we got to be careful here, folks, with our signs. We've got 6 minus 2 times negative 1. So that's going to be a negative 2. 6 minus a negative 2 would be a 6 plus a 2. Now let's look what's happening here. the negative 1 gets squared first. So that's going to become a positive 1, but I'm still subtracting it. So my vertex is at negative 1, 7. Let's make sure we're all good with that. Okay. This kind of thing caused some mistakes on the last take home. So, all right, find f of 0. The nice thing about the general form is when you plug 0 in for x, all the x terms are going to drop out instantly, and we can usually get the y-intercept pretty fast, 0, 6. So vertex negative 1, 7. Intercept 0, 6. Now we got to set the function equal to 0 to see if we've got any of the x-intercepts. Now usually when you have this kind of arrangement, we're going to go ahead and multiply both sides by negative 1, or move everything to the other side, however you want to think about it, to get x squared plus 2x minus 6 is 0. It's usually easier to try to factor something with a leading coefficient positive. So once again, there's two ways to think about what happened here. Either multiplied both sides by negative 1 and then distributed the negative 1 to each term, or you can think of it as I moved the x squared, the 2x, and the 6 to the other side. And now we try to factor. So we tried to split the x squared up into x and x. We're looking for factors of negative 6 that add up to 2. Now, it's important we're looking for factors, things that multiply to give us 6. A popular incorrect answer is 4 and 2. Those add up to 6. They don't multiply to 6. It turns out at this point we're kind of stuck. The factors of 6, at least the ones that we like, namely 1 and 6, 2 and 3, there's no arrangement of those that'll get us that middle term. So if that's the case, then we can always run it through quadratic formula. And over the years, there are all kinds of ways people have memorized this. They memorize. There's a little song that goes with it, a rap. There's all kinds of things. When I go to plug stuff into the quadratic formula, the first thing I'm going to do is I'm going to check out what's called the discriminant. The discriminant is this quantity here underneath the square root, the b squared minus 4ac. That's going to tell me what kind of answers I'm going to get if I'm going to get any. So let's look at the b squared minus 4ac. And I'm going to use this for my a, b, and c. So in this particular case, the a is a positive 1, the b is the 2, and the c is the negative 6. So in solving this equation, I'm going to use this for my a, b's, and c's. b squared minus 4ac. Once again, be careful of the signs here. I've got a positive 4 plus 24. That's a positive 28. That tells me I'm looking at two different, distinct, so that is what they say, real number solutions. Now I can just plug this into the formula here. Opposite of b is negative 2, plus or minus the square root of 28, all over 2a. In this case, a is 1, so all over that. Negative 2 plus or minus root 28, all over 2. Now, I want to take some time and walk through step by step how you simplify this. All right. But before I go to the next slide to do that, are there any questions on plugging the a, b, and c into the quadratic formula? So once again, you've likely seen quadratic formula before. It's something you should memorize. If you use it enough, you'll memorize it just because you use it enough. Okay? All right, let's talk about how to correctly simplify these solutions, because typically a lot of mistakes tend to happen attempting to simplify this. And it's good review of all things algebra. First off, let's talk about simplifying radicals. When you simplify radicals, you can simplify them by breaking them up over multiplication. So when you look at the square root of 28, you ask yourself, are there any nice perfect squares that are in there as factors? And the answer is yeah. 4 times 7, and 4 is a perfect square. So we can use properties of radicals. Square root of 4 is 2. So that simplifies the radical correctly for us. And now you notice I've got 2's, 2's, 2's. All right? How do you correctly simplify those? Well, there are two different ways to do that. Method 1 is you can always break up a fraction if you have sum or difference in the numerator. So you can always write this as a over c plus or minus b over c. Okay? Now you might be more familiar with this property going this way. You have the same denominator, you can add or subtract numerators. Here we're kind of going backwards, but we can do that as then negative 2 over 2 plus or minus 2 square root 7 over 2, and simplify it this way. And remember, this is shorthand for two solutions, negative 1 minus root 7 and negative 1 plus root 7. So that's one way to do it. The other way you can do it, simplify this, is you can factor. Factor out the numerator. What's common in both is a 2. So another way you could do this is factor a 2 out. You'd be left with a negative 1 there, plus or minus square root 7 there, all over 2. And then you can cancel that factor, and that'll get you right back there. The important thing is to realize that when you divide by 2, you're affecting both of these terms. Both of those 2's, not just one of them. Any questions on simplifying those answers? Now at this point, the square root of 7 is what we call an irrational number. The decimal representation of that neither terminates nor repeats. So we're going to leave it as the square root 7 stuff. We're just stuck with it. So my x-intercepts would be negative 1 minus root 7, comma 0, and negative 1 plus root 7, comma 0. Now, for practical reasons, you may want to approximate these. Let's think about the square root of 7. Well, it's got to be less than the square root of 9, but bigger than the square root of 4. So it's somewhere between 2 and 3. Okay? So maybe like 2.5-ish. So minus 1 minus 2.5-ish is like about negative 3.5-ish. That's ish there. Negative 1 plus root 7, that's like negative 2.5-ish. Excuse me. Not negative 2, but 2.5-ish. All right. So these would be the x-intercepts. And then this is us just trying to figure out where about they're going to be. Notice it's -1 plus root 7, -1 minus root 7. We have that symmetry about our vertex at, which is at -1 for that. So let's put all this together now. We got our vertex, our y-intercept, and now we got the x-intercepts. Vertex, -1, 7. Y-intercept 0, 6. And then the x-intercept's -1 plus or minus 2.5-ish. So 1, 2, and a little bit. 1, 2, and a little bit. And now I connect them with a pleasing shape. It's a quadratic function. The shape's going to be a parabola. So once again, it looks, that's an awful parabola. But we'll call parabola here. What's the domain, folks? These parabolas spread out left and right to cover everything. What's the range here? You're going to get everything up to and including the y value 7. That means we get a maximum of 7, but we get no minimum. If we imagine driving along this from left to right, we're going to be heading uphill from -infinity up to -1. And then at -1, we're going to switch and start heading downhill. Is it ever constant? Nope. Remember, these are x values. Any questions, folks? All right, let's plug this one into Desmos. Check our answer. So there's what a parabola looks like. There's our vertex. There's our y-intercept. Let's check the x-intercepts. Now, once again, these are approximations here. All right. Let's look at -1 plus square root 7, -1 minus square root 7, and compare that with the x value there. There's a -3.646, etc. Once again, irrational number goes off forever. 1.646. Once again, that's an approximation. So the exact values of the x-intercepts, we want to leave the root 7 in there, but we use the decimals to approximate it. And we approximated it, going 2.5 units each way. Okay? Any questions? All right. Let's look at some applications. One of the big applications of quadratics, well, there's two big applications. One of the big applications in the physics realm has to do with projectile motion. So if you take something like a rocket, launch it into the air, or if you throw like a basketball or something, the vertical distance off the ground turns out to be a quadratic in most cases, right? Ignoring air resistance and things like that. But out in the business world, one of the big applications of quadratic functions is profit. So let's think back. We had this last week, so this was last Tuesday, we had the cost to make t-shirts was given by this formula, and the price we charged per t-shirt was given by that formula. So this was given to us as a graph. We had actually come up with this formula, but there we go. So we got a couple new concepts this week. Revenue is defined as the number of things you sell times the price per item. So revenue is literally the money you bring in by selling your goods. So in this case, let's say I'm selling t-shirts at $5 a piece. If I sell 10 t-shirts, that would be what? 10 t-shirts times $5 a piece. They give me a revenue of $50. Now, what the revenue doesn't take into account is how much it costs to make and sell those t-shirts. That's where the concept of profit comes in. Profit is revenue minus cost. Now, the underlying assumption we're going to make here is that we make exactly the same amount of t-shirts that we sell. All right? So if I make 10 t-shirts, I'm going to sell 10 t-shirts. So if I make 10 t-shirts, I'm going to set the price to sell exactly 10 t-shirts. You follow? All right. So we're asked to find an expression for the revenue function and the profit function. So revenue, remember, is number of items sold times price per item. So R of X is the number of items sold. We're assuming that we're making and selling X t-shirts. So that's going to be X times the price. 30 minus 2X. Now you go through the distributive property there. You get 30x minus 2x squared. And this is good for x between 0 and 15. So that's our revenue. Okay. Any questions on getting the revenue? Now to get the profit function, we take our revenue and we subtract off the cost. So we're going to substitute in our expression here for the revenue and subtract off our expression for cost. So make sure that when you substitute, folks, we're using what? Make sure you use those parentheses there. Okay? Now, the cost function is good for any x bigger than or equal to 0. But the revenue function is good for only x between 0 and 15. So this profit function is only going to be good for x between 0 and 15. So we're going to simplify the profit function here in a minute. But do you see how the pieces parts where they're coming from? So we had our 30x minus 2x squared minus 2x plus 26 we can distribute that negative through. We have a 30x minus 2x squared minus 2x minus 26, so don't forget to distribute the negative in there. Let's write that first, the negative 2x squared. I've got 30x minus 2x, that's 28x minus 26. Any questions on getting the profit function? Take your time and write out each step. Don't forget to distribute negatives, things like that. Find P of 0. So P of 0. Now graphically that would be the y-intercept on the graph. What's it mean here? Well, if I plug 0 in, all the x terms are going to cancel out. I get a negative 26. That means when you sell 0 shirts, well, what's it mean if your profit is negative? You're losing 26 bucks. Now, 26 bucks should ring a bell. If you think back to a week ago, which seems like forever ago, remember that's your what? That was your fixed cost. So before you even started selling t-shirts, you had to buy the shirts, buy the markers, set up the stand, whatever. You follow? So that ties in with the concept of fixed cost. Solve P of x equal to 0 and interpret what the solutions mean in terms of profits and shirts. So here we go. So we had a negative 2x squared plus your 28x minus your 26 is 0. We've got x's in more than one place. We try to factor. Let's take out a negative 2 first. Remember, when you factor out a number, it's the same as dividing each term by that number. So we get a positive x squared there, a negative 14x there, and a positive 13x there, or a positive 13 there. And now I can factor. And sure enough, the factors negative 1 and negative 13 work out great. Now that I've got something factored against 0, I said each thing equal to 0. Well, the negative 2 is never 0, so don't worry about that. X minus 1 is 0, or x minus 13 is 0. So either x is 1 or x is 13. So what does that mean in terms of profits and shirts? So this says that when you sell one shirt, you're going to make $0 of profit. When you sell 13 shirts, you're going to get $0 of profit. So what's that mean? Well, remember, profit is revenue minus cost. So if the profit is 0, that means your revenue balances out your cost. So these are called break-even points. They're the points where you have to sell between this many amount to make any money. So if we think about what's happening graphically, and we'll fire this up on Desmos here in a minute, we're starting off sort of in the hole here at negative 26. If we sell a shirt, we've already recouped that loss, but we don't want to sell too many. So we want to sell between 1 and 13 to actually make a profit. Right? Because we know it looks like a parabola that's upside down. Use the vertex formula to find the vertex of the graph. Interpret what each coordinate means in terms of profits and shirts. All right, so here we go. P of x is negative 2x squared plus 28x minus 26. Using our vertex formula, negative b over 2a, or the opposite of b over 2a. The opposite of 28 over 2 times negative 2. That's going to give us a 4. To get the y coordinate, we'll plug 4 into the function. So what are we getting here? We got a 4 squared, that comes first. That's a 16. 16 times negative 2 is a negative 32. Plus 28 times 4. Well, let's see if we can make that a little easier. 30 times 4 is 120. 120 minus 8 would be 112. Minus 26. So 112 minus 32, well, 112 minus 12 would get us down to 100. Minus 20 would get us to be 80, so this would be 80 minus 26. 80 minus 20 would get us down to 60. 60 minus 6 would get us to 54. So we're getting 54. So what does that mean? So let's go ahead. We're going to use Desmos to dial this up. So we'll call this P of x negative 2x squared plus 28x minus 26. Now initially when you graph it, if you're on the standard window, you're not going to see it. It looks like I made a miscalculation here. What did I miss? That's 72. Oh, this is what I missed. I missed it right here. What's this? That's a what? 7. I had the wrong factor there. All right, let's fix this here. Yeah, this makes better sense. So here we've got negative 2 times 7 squared. So that's negative 2 times 49. That's a negative 98. Here we've got 28 times 7, which is what? 140 and 56, 196 minus 26. So that gets us down to what? A 170 minus 98. $170 minus 100 would get us down to 70, but that was too much, so that's a 72. All right, so now we're good. There we go. All right, so if we wanted to look at this here, we can adjust our window like we can with a graphing calculator. We only care about between 0 and 15 anyway. Right? We only care from 0 to 15 anyway. And we know we have to, well, that's actually a pretty good window there. So here we go. Let's label all these points. And we can kind of see what's happening here with this. So we start off with our fixed cost of 26. That means we're $26 in the hole. Then we start to sell t-shirts. As soon as we sell one t-shirt, we break even. All right? So the sale of that one t-shirt would break even. And then we would keep selling. Okay? Now, the more t-shirts we sell, what's that going to do? That'll increase the revenue, right? But also, the more t-shirts we sell, we're going to increase the cost. So we have this balancing act. So initially, the revenue, the additional revenue is outstripping the additional cost until we get to the vertex. So once, selling 7 shirts, to sell 7 shirts, you'd have to set a certain price. We'd get a profit of $72. If we want to sell beyond 7 shirts, we're going to have to keep dropping that price. At that point, the additional revenue we make doesn't make up for the additional cost. And so therefore we start to lose profit. If we try to sell more than 13 shirts, we're having to set the price so low that the additional revenue, or that the total revenue, gets wiped out by the total cost, and we end up actually in the red again. Okay? So that's kind of the story here. All right? So maximum profit is $72. When we're selling 7 shirts. All right. So we're going to be selling 7 shirts. What's going to be the price? What price should we charge to sell 7 shirts? Well, we plug that into our price function. 30 minus 2x. And that gives us, 16? So $16 a shirt. You'll sell exactly 7 shirts. If you only make 7 shirts, then you'll have your maximum profit of $72. Okay? All right. Last but not least, it says to find and interpret the average rate of change over the interval from 7 to 14. Okay, so if we look at this, let's go back here. Average rate of change over the interval from 7 to 14. Well, here we go. Let's remember what that is. Let's actually plot some points here. Let's plot 7 P of 7 and 14 P of 14. Remember what the average rate of change was. So the average rate of change is the slope that connects these two lines. So even though this isn't a linear function, I have these 2 points. I can still find the slope. So that would be P of 14 minus P of 7 over 14 minus 7. P of 14, we've got, that's negative 26 minus 72 over 7. So that's what? Negative 98 over 7. And negative 98 over 7 is what? 14? Negative 14. So remember, average rate of change is a slope. Think of that as negative 14 what? Well, the numerator here is profits. That's in dollars. So negative $14 per what? The inputs are shirts that are made and sold. So this means that on average, each additional shirt made and sold is going to do what? we'll lose $14 in profit. So we would start off with your $72 in profit, and on average, each shirt's going to end up costing us $14 in profit, until at 14, we've now not only lost all the revenue, we have additional cost incurred, and we're down at negative 26.